Okay, before we get started with today's lecture on Fourier transforms and Fourier optics, if you're interested, if you're not into this, so be it. But some of you might be interested to look at a Twitter account called @BardCalifornia, which I have used to publish a play. It is a play broken down into 280 character chunks. I have tweeted out an entire play, and it is a parody of Shakespeare, and it concerns a king, and that king is under investigation for colluding with the Tsar. And I really tried to work in a whole bunch of Shakespeare homages. We've got the characters from A Midsummer Night's Dream acting out their version of Pyramus and Thisbe. We've got Sir John Falstaff, knight errant from some of the Henry plays and the Merry Wives of Windsor. We've got Dogberry, the constable from Much Ado About Nothing, played by Nathan Fillion in the film version. And anyway, if you are curious to see some amusement that may be of some contemporary relevance, a king investigated for colluding with the Tsar, perhaps you will find it funny. And I am informed that the high schools teach precious little Shakespeare these days, but if you catch some of the Shakespeare references, you'll enjoy it more. And with that, let's talk about Fourier optics. So last Friday, I was talking about the fact that functions of two variables can be written in the form a of kx, or a double integral of a of kx, ky, e to the I, k dot r, dkx, dky, and a of k. I'll write a of k interchangeably from a of its two components. Integral of f of x, y, e to the minus I, k dot r, dA. And we interpreted e to the I plus or minus I, k dot r as a wave that's sinusoidally modulated and going in the direction of k. And then on Friday, I discussed the fact that if I've got an aperture and I look at waves that are traveling very far to a distant screen, so that we're talking about what's called Fraunhofer diffraction. Not all diffraction experiments involve, it's not always valid to make this approximation in a diffraction experiment. There are plenty of diffraction experiments where the detector is the object. But if the detector is far from the object, then these two paths are almost parallel, and the only discrepancy is down here. And if that's the vector r, which is the position of a point somewhere in the screen, here's an origin, and then here is some other point. This is theta, the angle that the rays are making with the axis. This extra pathway was length of r sine theta. And so the extra phase would be 2 pi over lambda length of r sine theta. And sine theta is cosine of 90 minus theta. And 90 minus theta is the angle between K and R. So that means that the phase difference, the phase lag or phase advance, depending on how you're looking at it, is just K dot R, because that's the length of K, that's the length of R, and that's the cosine of the angle between them. And you're thinking, no, it's the sine of an angle. Sure, but the sine of an angle is cosine of 90 minus that angle. And 90 minus the angle with the axis is the angle between K and R. Any questions? All right, so we put all this together, and we're just, in diffraction experiments, we're adding up the waves from every single point on the aperture, and they all come in with a different phase shift. So the electric field on your detector winds up being proportional to the Fourier transform of the aperture. And I'm writing proportional to because there's a bunch of constants that would matter if you were trying to get a precise calculated value. If you're actually trying to figure out, well, am I going to measure, 1 microwatt of power per square millimeter here, or 10 microwatts of power per square millimeter. But if I just want to figure out where are the peaks, where are the minima, and where are the points halfway in between, then all I need is the Fourier transform. So that's just the integral over the aperture of e to the minus I k dot r dA. And on Friday, and this is in the solutions to Friday's assignment, first I had you just do the Fourier transform of a square. The side lengths of the square are a, then we get that the Fourier transform is a squared sinc kx a over 2 sinc ky a over 2. But let's say that instead we've got a rectangular aperture with a height b. Then your Fourier transform is AB sinc kx a over 2 sinc ky b over 2. And what that means is that the width of your diffraction pattern is inversely proportional to A and B, because if we look at the Fourier transform, we're going to get a bright central spot, and we're going to get somewhat smaller off-center spots, and then smaller and smaller still, and smaller still, and there's also spots out here. And our first node happens when kx a over 2 equals pi. So kx equals 2 pi over a. And our first node going up happens when kyb over 2 equals pi. So ky is 2 pi over b. So basically, if you've got something that's wide or in the x direction and narrow along the y direction, you get a diffraction pattern that's wide along the vertical direction and narrow along the horizontal direction. Your Fourier transform is in some sense an inverse of your shape. All of the dimensions, sort of the aspect ratio gets reversed. Questions? These ideas have a lot more applicability than just predicting what happens in a sophomore or junior lab where you've got some rectangles and you put them in front of laser beams and look at the color of the spots. For starters, this is how we work out the structures of solids and molecules a lot of the time. We put those solids or molecules in an X-ray beam, and then we see how the X-rays get diffracted. And essentially the spacing between peaks is inversely proportional to the spacing between atoms. And so the larger the spacing between peaks, the smaller the spacing between atoms. And there's a lot more to it than that, but that's the beginnings of the idea. And you essentially do an inverse Fourier transform, and you can work out the structure of a molecule or the structure of a solid. And obviously this gets used all the time in chemistry, it gets used all the time in material science. I can only assume that right now a whole bunch of people have various COVID viral proteins in synchrotron beam paths, and they're scattering X-rays off of those in order to figure out what are the structures of these different molecules, what are the structures of these molecules when we put them in an aqueous environment versus when we put them in a more lipid-rich environment. What are the structures of these proteins at different salt concentrations? All of these things matter. Any questions? Now, we also talked on Friday. I had you do some scenarios where we considered, and we only did 1D here, but we considered an aperture that had maybe 3 segments to it. And the light gets phase shifted. So maybe here the light gets multiplied by +1 as it goes through, which just means it goes through either 1 full cycle or 2 full cycles or 3 or 3,000 full cycles. But here it gets multiplied by -1 because it goes through an extra half cycle. And I had you compute the Fourier transform of that. And we did that in 1D. The integral from, it would just be the integral across the entire aperture of T of Y. T is the transmittance, e to the minus I k y dy. And so that winds up being the sum of 3 sinc functions. Each with possibly a different width. If this one was A, and I didn't draw any of this to scale, but if this was A over 2 and this was A over 2, then you'd have to account for that in the sinc function. And a different phase factor. And that phase factor would be e to the I times e to the minus I k times delta y, where that is the center coordinate. And this idea of making custom masks that where you get different phase shifts on different parts of it, that gets used in a lot of places. One place it gets used in my area of research is to shape beams in microscopy, to produce beams that have special profiles so that you can focus the light to unusual shapes. A consumer application, a few years ago, there was this thing, it's probably still out there, where there were these toys that if you looked at their reflections, you would see the shapes of Christmas trees. You basically got a diffraction pattern that was the shape of a Christmas tree or a reindeer or Santa Claus. My nephews had some of those. I assume they're still on the market. Somewhat more serious application would be adaptive optics. People can make, instead of making a mask that has a fixed phase pattern, They could either make a mask where you apply a different voltage to each element of the mask, and that voltage changes the optical properties. It changes the index of refraction so that you get different delays on each one. Or you could do this experiment in reflection mode. You could have essentially adjustable mirrors where you change the mirror height on each step. And by changing the mirror height, you change the distance that light travels. And you're thinking, I've drawn this in a really exaggerated way. So what's actually happening here, you don't have to worry about that too much. This is a very exaggerated view. But essentially, the light reflecting off of each of these undergoes a different delay. This gets used to do adaptive optics to correct for the atmosphere. Contrary to what people like to tell themselves, adaptive optics was not invented to look at the stars. It was invented to track satellites and to take very good pictures of satellites. And then civilian basic researchers were allowed to think that this was invented and commercialized for them to do noble things like basic research on the stars. But no, it was invented to look at things that are flying in space and have Cyrillic letters on them. And the Russians probably invented something similar to look at things that are flying in space and have Latin letters on them. So let's do a 2D example of that. Let's consider something very simple. A rectangle that has height A and width 2A, and one half of it, the transmittance is +1, and the other half of it, the transmittance is -1. And so we're going to be taking the Fourier transform of that. Now the center is going to be at the origin. And the Fourier transform of each of these things is a sinc function. Okay, so our Fourier transform is going to be, and I'm going to write down some sinc functions with a lot of space in front of them. We know we're going to have products of sinc functions. We're going to have sinc of kx a over 2, sinc of ky a over 2 from the first, let's say the left, plus sinc of kx a over 2, sinc of ky a over 2. And in front of all of this, both of those sincs should be multiplied by an a squared. So we know that because we got two squares, we're going to get two sinc functions. And because these squares have the same dimensions, they're both going to be sinc of kx a over 2 and ky a over 2. But if all we were doing is adding up the same product of sincs twice, then we just get 2 times that sinc. Is that all it is?
I really want to say yes.
What?
I want to agree with you.
Well, let's see. For starters, one of these gets multiplied by -1. Okay, the waves coming from the right got flipped upside down. So we've got to have a minus sign right there. We know that much. And furthermore, we know that they get shifted, okay? They get shifted along the x-axis. So one of these is going to have a phase shift of e to the minus I kx, well, let's see here. This is going to be x equals minus a over 2, and this is going to be x equals plus a over 2. So it looks to me like this is actually more complicated, because We multiply each of them by a phase shift, and one of them, the phase shift winds up being positive, and the other one is just negative. And so we get a squared. I'm going to factor out all of the common factors right now. Sin kx a over 2, sin ky a over 2 times e to the I kx a over 2 minus e to the minus I kx a over 2. Which is 2i sine kx a over 2. Now you may be worried, wait, can the Fourier transform be imaginary? Sure, the Fourier transform can be imaginary. It's an odd function. If I multiply this odd, it's an odd function of x because it's +1 on one side, -1 on the other side. So when I flip the value of x, when I multiply the value of x by -1, the function gets multiplied by -1. And you may be thinking, well, not necessarily. Over here it's 0, and over here it's 0. That's true, but if I go from here to here, I multiply 0 by -1. And to quote Nathan Fillion, let's see, nothing times -1, carry the nothing, that's nothing. So minus nothing is nothing. So yeah, going from here to here, I multiply by -1. Going from there to there, I multiply by -1. I've got an odd function of x. And when I multiply that odd function of x by e to the I times k, e to the I kx times x. Let's see, I get a cosine. Cosine multiplied by odd is odd. So everything involving the cosine, the real part, that's going to integrate to 0. On the other hand, I've also got a sine. So I take an odd function and I multiply it by sine. Sine is also an odd function. Odd times odd is even. So I've got an even function. And even functions don't usually integrate to 0. So my imaginary part is even. Questions on that?
So if instead of like 1 and -1, if it was 1 and -2, so that they weren't equal, would you get a mix of cosines and sines instead of just the sine?
Oh, if it was 1 and -2 instead of 1 and -1. Yeah, if I have a function that's neither even nor odd, then the integral is going to be messy. Even functions have nice properties. Odd functions have nice properties. They're both symmetric. But functions that are neither even nor odd are messy. Now, another thing that people may be wondering is, hey, how could I have that this Fourier transform is imaginary? I mean, okay, fine. The math checks out. The integral comes out to an imaginary number. But what does it mean? Well, what it means is that my electric field will be proportional to I times some sinks and sines times e to the minus I omega t. I've been leaving that out in this model, but if I were to actually calculate the electric field, there would be an e to the minus I omega t. It would be proportional to the real part of all that. And you're thinking, well, it's imaginary. Isn't the real part 0? No, because what I've got is the real part of sinks and sines. Should be sinks and sines, not sinks plus sines, times I cosine omega t plus I times minus I sine omega t. So all it would mean is that my electric field is proportional to sine of omega t. There's no rule of the universe that says that that's not possible. I don't expect you to, in just a couple of classes, become experts on Fourier optics, so I'm not going to test you on the details of electromagnetic waves with complex parts. But what I do expect you to know is that imaginary numbers can represent things that we measure in the lab, because the imaginary number just means that whatever we're measuring got phase shifted. That instead of being a cosine function of time, it's probably a sine function of time. So if you see an imaginary number, you should not react to it like a vampire seeing garlic and a crucifix, okay? All it means is that something got phase shifted in the lab. It doesn't mean that we've abandoned physical reality. Any questions? Going once, going twice. Well, that was an example with two things displaced from each other along the x-axis. Now, what if I had two squares stacked on top of each other vertically? In general, the effect of a phase shift is to shift everything. If I shift a function, if I go from f of r to f of r plus delta r, then what I get is I get the double integral of f of r plus delta r e to the minus I k dot r dA. Let's do a u substitution. U equals r plus delta r. So ux equals x plus delta x, uy equals y plus delta y. Dux is still just equal to dx, duy is still just equal to dy. So dA is just dux, duy. Nothing changes there. But r is now u minus delta r. So my integrand changes, and now I get the double integral of f of u e to the minus I k dot u minus delta r and this is, I can pull out this factor. It doesn't depend on u. So I just get e to the I k dot delta r which looks exactly like a of k with a few names changed. And that which we call a, that which we call u would by any other name still be a coordinate vector. You notice how much I like Shakespeare, that I would actually sit down and write a 5-act play and tweet it as a parody. And I would quote Shakespeare every time I change variables in math. Okay, so this is exactly what we had before for Fourier transforms of single variable functions generalized to two variables. We learned that if we had a function of one variable and we shifted the function, we got a phase shift in the Fourier transform, e to the I k times whatever distance we phase shifted. Well, now in 2 dimensions, we've got e to the I k vector dotted with our displacement vector, delta r. Any questions on that logic? So in this example here, we've got two sinc functions. All right, because we've got two squares, because we're adding up two squares, we're going to have two sinc functions. The question is, what do each of those sinc functions get multiplied by?
E to the I k x a over 2.
Why kx? Does anything get shifted along the x direction here?
Oh, is it iky?
It's going to be iky because now the shift was along the y direction. Before, in the previous example, yeah, the shift was along the x direction. So k dot delta r would be kx a over 2 or minus kx a over 2, depending on which way we're going. But here, it's going to be ky. Delta r is plus or minus a over 2 y hat. So k dot delta r is going to be plus or minus ky a over 2. And then on your problem set, I give you a problem where we divide up into 4 squares. Some of them have transmittance +1, some of them have -1. And now delta r, I forget whether I called the widths a or a over 2, but whatever, it's going to be plus or minus some distance times x hat plus or minus some distance times y hat. Any questions? One thing that people wonder is, okay, how often does this show up in practice? Because when do you really have an infinite distance or very, very, very long distance from source to detector? And there are lots of problems with that. I mean, for starters, you have to build a very long beam path. Sometimes that's natural, sometimes it's not. If you have a long beam path, light can spread out. You could lose a lot of signal. But we don't actually need to do that. Remember, the idea is that in all of these approximations, parallel rays meet at infinity. Well, there's a much easier way to bring parallel rays together. And that's to have a lens. And what a lens does is it brings parallel rays together in the focal plane, one focal length away. So parallel rays meet in the focal plane. And that's why people often call the focal plane the Fourier plane. Because in the focal plane, parallel rays meet, which means that we are taking the Fourier transform of the pattern of light that came in. And so a lot of experiments in Fourier optics are done in labs that don't have really, really, really long beam paths. They just have something in front of a lens, and then they have their detector one focal length away, and that focal plane is called the Fourier plane. Any questions?
In order to make the Fraunhofer approximation, we need a long path, but how long of a path do we technically need, considering that the diffraction pattern is kind of very small? Wouldn't, you know, not so long of a path be able to make the approximation?
It's really a question of how long is the path relative to the aperture size. Basically need your path to be long enough that a ray going from the bottom of the aperture to your detector is almost parallel to a ray from the top of the aperture. So it's not a question about this angle. It's really a question about this angle, right? If the angle between rays from the bottom and top of your aperture going to a point on a detector is small, then you can get away with it. So it all comes down to that angle. And I would say that if your distance from the detector is maybe 10 times your aperture size, then it's going to be an okay approximation. If it's 20 or 30 times, it's going to be a really good approximation. So like the Fourier transform of a pinhole, just about always good. Diffraction gratings, generally you're illuminating a diffraction grating with a laser spot that's a few millimeters. So if you're even a couple centimeters away, if you're less than a centimeter away, you'll still get a diffraction pattern. The quantitative details of it might not perfectly match up with Fraunhofer predictions, but a lot of the qualitative things about peaks and troughs will still match up. And once you're a few centimeters away, you'll get very, very good quantitative agreement.
Okay, thank you.
You're welcome. Any other questions? Let's say a little bit about diffraction gratings, okay? We'll just do 1D diffraction gratings, but 2D diffraction gratings are fun. There was this one time in grad school, I made a bunch of stamps that, this is back when I was still doing experiments. I thought I was going to do some other completely unrelated experiment, but it meant that I had to make a bunch of pieces of transparent rubber that had features that were evenly spaced about 10 microns apart. And so if I shined a laser on them, I would get really, really nice diffraction effects that basically looked like a disco ball. All right, you know, the pattern of speckled light going all over the room was really amazing. So, diffraction gradient. Call this D, I'll call this A. And we know that each of these is going to produce a diffraction pattern. It's going to produce a diffraction pattern that's a sinc function. So we're going to get sinc of Ka over, well, Kya over 2. But they're each going to get a different phase shift. Times e to the I Ky times y. So here y equals 0, y equals d, y equals 2d, etc. So really I should be writing that as the sum over all the slits, e to the I ky times y, or sinc Kya over 2, sum of e to the I kd, I'll just write it as kyd times m. Or I could write this whole thing as raised to the power m. Now, we know that if this exponential, excuse me, is anything other than 1. Let's say that it's this, all right? It's got some angle phi, right? This is a complex number. This is e to the I KYD. It's just a point in the complex plane. Well, here's its square. It's making an angle 2 phi. Here's its cube. It's making an angle 3 phi. Here's its fourth power, 4 phi. Fifth power, sixth power, seventh power, eighth power, ninth power. We're right back where we started. See how we've done a full circle? Well, if I add up all those evenly spaced points on the edge of a circle, so what I can conclude is that if KYD is not equal to 2 pi times an integer, then my Fourier transform is 0. Any questions on that reasoning? But what if KYD is 2 pi times an integer? Let's see, e to the I KYD is equal to 1. And e to the I KYD to the power m, 1 times 1 times 1, hang on. I haven't watched it enough to do the Nathan Fillion impression, never mind. 1 to the m, as long as m is an integer, is 1. So my Fourier transform is 1 plus 1 plus 1 plus 1. It's infinity. Here I've got something that's equal to 0 for all inputs except for a special value. What must that be?
The direct delta function.
Yep. So this is delta of KYD, because if KYD is 0, it's infinity. But wait, if KYD is equal to 2 pi, well, then it's also infinity. And if KYD is equal to 4 pi, it's infinity. So what I've got is sinc of KYA over 2 times a sum of delta functions. Any questions?
What was the condition that allowed you to say the Fourier transform was the addition of 3 Dirac functions?
Oh, it's way more than 3. I did plus more dots, etc.
Oh, okay, that's cool. But because in my head I see that the Fourier transform, if I'm mistaken, or I may be mistaken, is what I'm trying to say. The Fourier transform of f of t e to the I k x is equal to 1, correct?
The Fourier transform of a sinusoid is a delta function. And the Fourier transform of 1 is also a delta function. All right. So the Fourier transform of 1 is delta of k. The Fourier transform of e to the I k naught x is delta of k minus k naught.
Okay. Okay.
And 1 would just correspond to the case where k naught is 0, because e to the I times 0 times whatever is nothing times something carried to nothing, nothing. So we got e to the nothing, which is 1. Other questions? This is why the fact that the Fourier transform of a diffraction grating is just a bunch of delta functions is why when you shine a laser on a diffraction grating, you get a bunch of small, intense spots and nothing in between them. And you could say, well, now technically, it's not actually a bunch of infinitely small spots. The intensity is not infinity. And you're right. The intensity is not infinity. The intensity is finite because the diffraction gradient is finite. We don't sum over an infinite number of slits. We sum over a finite number of slits. And if you take an optics class, then we would go into the details of what really shapes the width of that. What I want you to take away here is that the Fourier transform of a periodic function is a bunch of delta functions. Now, a lot of the times in optics, we aren't dealing with square or rectangular apertures. A lot of the times in optics, we are dealing with circular apertures. There are two ways to compute the diffraction pattern of a circular aperture. One is to ask Zemax to do it. That's the computer program that we're going to use next semester in applied optics. It's what they use all the time to model the diffraction limited resolution of a circular lens. The other way to do it is to recognize that we are still just doing an integral over an aperture, only now we're doing an integral from r equals 0 to, and this was not my idea, but everyone calls the radius of a circular aperture a. And yes, this is endlessly confusing because the width of a square aperture is a. So you think of a over 2 as the half size. But then they go and say, hey, half the size of a circle will be a. Not my idea. I just work here. E to the I k dot r r dr d phi. And now we've got a little bit of a problem because the r vector in the plane will be r cosine phi x hat plus r sine phi y hat. And k dot r will be, well, let's see here. K has three components, excuse me. K has two distinct parts that we need to think about. There's the part of K that is in this plane, right? So if K was going that way, that's K, all right? There's the part of K that's out of the plane, KZ. And then there's the part of K that's in the plane. And K in the plane has its own angle, which I'm going to call phi sub K. K in the plane makes an angle if this is the x-axis in our plane. All right, so K dot R has got to be the length of K, the length of R, times the cosine of the angle between them. Which is just going to be the length of K times the length of K times R times the cosine of phi minus phi sub K. All right. I'm going to say for convenience that phi sub k is 0. It doesn't really change anything. If you don't want to do that, then we could do a u substitution. We could say that phi is phi minus phi k is equal to u. All right. Well, d phi equals du. So k dot r is the length of k times r times the cosine of u. And what we're left with is the integral from r equals 0 to a, the integral from u equals 0 to 2 pi. You could say, wait, shouldn't you start from somewhere else? Well, sure, but we go around the whole range of values regardless. So if I started from something else, I go out to 2 pi plus something else. Nothing really changes. And actually, I'm going to reverse the order of these only for convenience in writing things out. And since starting 2 weeks from now, we're going to be talking about what are called special functions, it's worth dwelling on what the idea of a special function is. This integral has a name. This integral is called a Bessel function. And when I call something a Bessel function, I say, hey, this integral is equal to a Bessel function, people worry. They say, but what's a Bessel function? What kind of function is it? And one thing I could say is, well, it's the function you get when this is what's called J naught of KR. That's what you get when you integrate e to the I KR cosine u du. Okay. Or if you don't like the idea of two symbols, J naught of x is the integral from phi equals 0 to 2 pi e to the I x cosine of u du. And you say, but what is that? I mean, you're just cheating here. You're just saying, hey, I've got an integral that I don't know how to do. So I'm just going to say, all right, I've given that integral a name, and there, we're done. I named it. I baptized this integral in the name of Newton and of Leibniz and of, I don't know, who would be the third in a trinity of mathematicians doing calculus. You know, I baptized this integral in the name of Newton and Leibniz and Hilbert, and hereby name it Bessel function, okay? I could do that, I could name it. And you say, that sounds like cheating. Well, it's not really cheating. I mean, look, what is a function? A function is something that takes a number as an input and spits out another number as an output. Number in, new number out, okay? So I could plug in 37 for KR, and I could do that integral, e to the I 37 cosine of u. And I'd probably have to do that integral with the computer, adding up little values, you know, evaluate it for this value of the angle u, then evaluate for another, evaluate the integrand for another value of the angle u, and then for yet another value of the angle u, and add up all of these things. And then somebody says, well, I don't want to do it for 37. I want to do it for 0.36. So I plug in 0.36 for KR, and I add up all the different values of that integrand for all the different angles and get a number. But the end result is that number in, number out. That's a function, okay? Now, we don't just say, hey, I baptized this integral with this name and declare it done, amen. I mean, people have actually studied that integral. People have compiled values of that integral and put it in tables. People have compiled values of that integral in computer programs and plotted them. And we'll do that in a minute. And what's in the chat? Anyway, so you can look at it that way. I mean, think about it. Sine and cosine. We sit here and say sine and cosine are functions, but other than a few special angles like 0, 30 degrees, 45 degrees, 60 degrees, and multiples thereof, we don't know how to write down the value of, sine of 73 degrees. I have no idea what the sine of 73 degrees is. I could sit here and say, well, it's got to be between 0.7 and 0.83 and start approximating how close it is. But, I don't know what the sine of 22 degrees is. I'd have to approximate it. All right. Well, likewise with this integral, it would be a harder thing to approximate. But if we studied more properties of it, if we learned the Taylor series for that Bessel function, we could do it. Just like once we learned the Taylor series for sine and cosine, we could do it. So this is just a function. And it's a function that we're going to see in a couple weeks, because besides being the value of this integral that shows up in the theory of Fourier transforms, it also turns out to be the solution to a very important differential equation. Basically, a special way of writing out the wave equation. So let's go into Mathematica. I've got a Mathematica notebook that I created for the last topic, which I hope we'll get to today. But let's just plot that function. It's called a Bessel function. Bessel J of 0x, x from 0 to, I don't know, 8. All right, there it is. It looks like, you might say, oh, is that a sine? No, it's not a sine because it keeps decaying. You could say, is it a sink? Well, it looks a little bit like a sink, but it's not quite a sink. One way to see, it's not a sink squared because sometimes it's positive and sometimes it's negative. It turns out that let's plot it for a wide range of values. Let's plot it out to 40. And I'm going to plot to show you that it's not, that it's actually very different from a sink. I'm going to plot sink of x. And you see that sink decreases very rapidly. It decreases more rapidly than the Bessel function. It turns out that it actually decays not as sink x, but as sine of x over square root of x. This is just a fact that I'm asserting for now, but it's a fact that will become more salient in a couple weeks when we start talking about the solutions to the Bessel equation. And we could take this out even further. And you see that the sink function, sorry, the Bessel function and the sine of x over square root of x remain fairly close to each other. They start to differ, well, they differ kind of systematically, but the differences are decreasing. And that might not look at all easy to interpret, but sorry. Let's go to 500, 490 to 500. They wind up being pretty close to each other, and their ratio doesn't change much. You know, there's some factor of square root of pi or square root of 2 or square root of pi over 2 that I'm leaving out, but they basically get pretty close to each other, right? And so it's this function that oscillates, and it has some wave-like properties, and it's the solution to that integral, right? And so if you take nothing else away, well, what questions do you have on the Bessel function right now? Let me stop there. Somebody must have a question. Nobody has a question?
Maybe.
If someone else has a question, please ask. I'm still forming mine.
Like the usual question, real life applications of it.
Fourier transforms of circular apertures, and circular apertures show up in lenses, telescopes. So that's pretty important. It's used, it turns out, as we'll learn in a few weeks, that it's a solution to the wave equation. So if you want to solve the wave equation in a circular domain, whether that's to study the vibrations of a drum, or if that's to study an electron confined in a circular system, which people make in nanostructures these days, then you have to solve a wave equation there. So anytime you have waves in a circular situation, whether it's diffracting through a lens or a wave confined to a circular drum or an electron confined to a circular region, the Bessel function shows up there.
In
So-
practice, do people use the Bessel function, or do they approximate it as a sinc function like you're demonstrating right now?
There are many cases where people use the Bessel function. I mean, a good portion of my thesis was on using something called spherical Bessel functions, which are used to model the scattering of light from spherical particles, which shows up all the time in atmospheric science. It shows up in colloidal science. Spherical particles are a good model for dust grains in the atmosphere. They're a good model for a lot of microscopic particles in biology. They're a good model for dust grains in space. And so you will, like, in my thesis, in the section on scattering of light from special kinds of spherical particles, I was using spherical Bessel functions in citing papers from astrophysics and biology and atmospheric science, because they all use this to model scattering from spheres. So just as there are the regular Bessel functions that I'm talking about, very, very close to them are the spherical Bessel functions, which I might give you a little bit about later in the semester, I'm not sure, but the Bessel functions are a prerequisite for understanding the spherical Bessel functions. Then there's something called the MIE solution, M-I-E, which is used to model exactly the scattering of light from a spherical particle. And that winds up requiring that you sum an infinite series of Bessel functions or spherical Bessel functions. In practice, people will sum that series out to maybe a few dozen terms. Other questions?
Are you telling us that the Fourier transform of the Bessel function, no, just e to the ikr cosine of u is a sinc function?
No, I said the whole way along that it's not a sinc function. I said that the integral of e to the I times kr cosine u is the Bessel function of kr, and that the Bessel function is not a sinc function. Because remember, we plotted here, I'll plot three things. I'll plot sinc of x on here, and then I'll put in plot legends Bessel sinc and sine x over square root of x. All right, and you see that the sinc function decays much more rapidly.
Mm-hmm. Okay, cool.
Now, if we go back to the integrals I wrote down, going to do right now, you notice we only did half of it. Now we still have to figure out the full Fourier transform. We just did the Fourier transform really of a ring. Okay, we just did the Fourier transform of at one particular value of R. So we've only done the Fourier transform around maybe here. We haven't done the Fourier transform of the entire thing because we only integrated over angle. All right, that's a fixed R. If I want to integrate over the entire circle, I have to integrate over this ring and this ring and this ring and that ring and that ring. So I have to now take that Bessel function, multiply by R, and integrate. And until we really study the properties of Fourier of Bessel functions in detail, it's all just assertions. And you'll notice that the book basically makes assertions too. It says, hey, we do these integrals over circles, but these integrals over circles are also called Hankel transforms, and we get out Bessel functions. And all I'm going to put on the homework about Bessel, well, I'm going to put some stuff on the homework about Bessel functions to have you work out those properties very gently. I'm not going to have you, just memorize and then regurgitate some of those properties. But if we were to integrate that, if we were to integrate Bessel J of 0 k times R going from 0 to A, we would get something that looks like that. We would get basically a Bessel function, we would get a Bessel function, a different Bessel function, something called the first order Bessel function divided by K. I don't expect any of that to make a whole lot of sense to you right now, but I just want you to know is that integrals of Bessel functions often wind up being Bessel functions. And if we were to plot the intensity profile, if we were to plot Bessel J of 1K divided by K, whole thing squared, K from 0 to 2 pi, we would get something that looks like that looks like the Fourier that looks a lot like a diffraction pattern. And you might be thinking, oh, so that's a sinc function. Nope. That one's a little bit closer to a sinc function because it's squared, but that itself is not a sinc function either. They're normalized it so it peaks at 1, and we could verify that. And I could also square the sinc function, and they look somewhat similar, but you will see that they're not really the same. Oh. The Bessel function winds up decaying more rapidly than the sinc. Everybody just wants it to be the sinc. They want it to be a function that you already know, but these really aren't. They are their own functions. So here's what I want you to take away at this point. I want you to take away that as soon as we start Fourier transforming circles, we get very complicated functions that have their own properties. Fourier transforms of circles are important because they explain how waves spread out when they pass through circular apertures. Circular apertures show up on, say, microscopes and telescopes. They show up when scattering light off of spherical particles, which explain things that happen in the atmosphere. They explain things that happen in nebulas. They explain things that happen when light passes through tissue. They explain anytime light interacts with a round particle. Any questions at this point?
So this, the resulting Bessel function is the diffraction pattern, right?
Yep, the Bessel function is the diffraction pattern. And if you want to go beyond saying, hey, look, it's got this weird shape, we look up this function in a book to understanding what it means, that's part of why we will be doing Bessel functions in detail in a couple weeks.
And if this is part of the, if this represents the diffraction pattern, then how does that look like visually? Because I know, of course, this seems one-dimensional or two-dimensional, I guess, like the way we're graphing it. But of course, the diffraction pattern should be like circular, if you know what I mean.
Fair question, totally fair question. Let's see, I'm just going to define a function. I'm going to say g of x, g of kx, ky is defined as 2 times Bessel j of 1 square root of kx squared plus ky squared divided by that whole thing. I don't squared, and then I'm going to divide by the reason I'm doing it like this is because I don't want to calculate a square root and then square it, because square roots are very slow to calculate. Kx, let's say minus 4 pi to 4 pi, and ky minus 4 pi to 4 pi. And I never closed that. And that is a very bad, poorly sampled rendition. It's missing the circular symmetry because it's an attempt to represent in that is what it looks like. You see a peak, and then if you look very carefully, you can see some faint rings around here that indicate that there are secondary peaks. I tried to do a density plot and I force it to show the full range. You see a bright peak and very faint rings on the edges. Any questions?
I have a question. Since graphically it kind of looks like the sink, is it related to like the top hat function?
Not really, no. It's because the top hat function is the Fourier transform of something that's flat in one dimension. This is the Fourier transform of a circle, something that's 0 outside of the circle and 1 inside the circle. But if you take nothing else away today, Bessel functions are not sinks. I know that qualitatively they vaguely resemble it, but Bessel functions are not sinks. Bessel functions are Fourier transforms of circles. They show up whenever you've got waves in circular geometry. Hence, they show up when we Fourier transform a circular aperture. And a few weeks from now, we're going to solve the wave equation in circular geometry we're going to get Bessel functions. This is why. And if you write down a sinc function when we solve the wave equation in circular geometry, and we're supposed to be using a Bessel function, I will cry. On Wednesday, before we start differential equations, we're going to talk about one last Fourier topic called aliasing. And aliasing is best understood in terms of this thing that you see whenever you watch airplane propellers or helicopter blades on TV. That thing hasn't actually slowed down, but it almost looks stationary briefly. And the reason is that you're sampling, I don't know for sure what this frame rate is, but usually the frame rates are like 25 frames a second, 24, 25 frames a second. Well, if the propeller is moving in such a way that every 25th of a second, it's in the same position. So you take a picture, take a picture, take a picture, take a picture. If it's at the exact same position every 25th or whatever of a second, then you're not going to see it move. You're only going to see it move if it's at different positions in different frames. But as it increases its rotational speed, its angular speed, sometimes it just happens to line up with the frame rate of the camera. And that shows up in a lot more than just weird special effects with video of airplanes and helicopters. And we're going to talk about that next time and what the implications are for measuring something, for measuring a signal and accurately recovering the Fourier transform. And with that, I am done for today. Have a good day.
Dr. Small, I wanted to ask one last question about the Bessel function. That looked like an airy disk. Would that be wrong to draw that in?
That is an airy disk. An airy disk is a first order Bessel function divided by its input.
Okay. Okay, cool. All right. Thank you, Dr. Small. I'll see you soon.
You're welcome. Ewan, do you have a question?